Welcome to Mysteries of the Universe. I'm your host, Ben Carter, and in today's episode we uncover a profound and unsettling truth about the cosmos. Everything we can see, every star, planet and galaxy, makes up only a tiny fraction of what exists. The rest is something we cannot see, cannot touch, and cannot fully explain. It is invisible, yet it holds the universe together and tears it apart. The story begins nearly a century ago, with the quiet revolution of astronomical observation. In the 1920s, astronomer Edwin Hubble made a discovery that would alter humanity's place in the universe forever. By studying the redshift of light from distant galaxies, Hubble revealed that the universe was expanding. Galaxies were moving away from one another, carried by the stretching fabric of space itself. This was a groundbreaking shift from the static universe once envisioned by Einstein. But hidden within this revelation was a puzzle far stranger than anyone anticipated. Decades later, in the 1930s, another astronomer, Fritz Zwicky, turned his telescope toward the Coma Cluster, a massive gathering of galaxies located over 300 million light-years from Earth. He was trying to understand how such a colossal system could stay together under the pull of gravity. Based on the visible matter, the stars and galaxies he could detect, there simply wasn't enough mass to account for the gravitational forces holding the cluster intact. Something was missing. Zwicky called this unseen influence Dunkel Materie, dark matter. At the time, his idea was largely ignored. It seemed implausible that so much invisible mass could exist undetected. But the mystery refused to fade. In the 1970s, Vera Rubin and Kent Ford made observations that brought Zwicky's findings into sharper focus. Studying the rotational speeds of galaxies, Rubin noticed something peculiar. The stars at the outer edges of galaxies weren't moving more slowly than those near the center, as Newtonian physics would predict. Instead, they were moving just as fast, as if held by some invisible gravitational force beyond the reach of light. The galaxies, it appeared, were enveloped in massive halos of something unseen. This was no longer a minor anomaly. It was a challenge to the fundamental laws of physics. The data was consistent, repeatable, and undeniable. There was more mass than could be accounted for by everything that glowed, radiated, or reflected light, and not just a little more, much more. Over time, astronomers calculated that visible matter makes up less than 5% of the total mass-energy content of the universe. Roughly 27% is made of this mysterious dark matter. But even that, as vast as it sounds, is overshadowed by something even stranger. In the late 1990s, two independent teams of scientists were measuring the rate at which the universe was expanding. Using type Ia supernova, stellar explosions that act as standard candles, they expected to find that the universe's expansion was slowing over time, tugged back by gravity. But what they discovered shocked the scientific world. The expansion wasn't slowing, it was accelerating. There was no known mechanism to explain this. Something was counteracting gravity on the largest scales imaginable, a repulsive force driving galaxies apart faster and faster. This force was given a name, dark energy. It couldn't be seen, couldn't be touched, but its effects were measurable across billions of light-years. Dark energy, according to current models, comprises nearly 68% of the universe. Combined with dark matter, this means that more than 95% of the cosmos is made of something we do not understand. The implications are staggering. We live in a universe where the stars, the planets, the nebulae, all the things we consider the universe, are only a faint trace of the true structure. The overwhelming majority of the cosmos is invisible, interacting only through gravity or unknown forces. It does not emit or absorb light. It does not clump together in ways we can easily track. And yet it controls the fate of galaxies, dictates the expansion of space, and shapes the ultimate destiny of everything that exists. What began as a few unexplained motions in distant galaxies has now become the central mystery of modern cosmology. Not because we lack data, but because the data has shown us something we never expected to find. The universe, it seems, is not made for our eyes. It is a shadowed place where the most important structures lie hidden from view. With the scope of the mystery now fully realized, astronomers and physicists turn to the task of collecting more data. searching not just for confirmation of dark matter and dark energy, but for any clues as to what these invisible forces might be. The universe, fortunately, offers a kind of record book written in light and gravity, and modern instruments have allowed scientists to read it with astonishing precision. One of the most revealing sources of information is the cosmic microwave background, or CMB. This faint afterglow of the Big Bang, discovered in 1965, is the oldest light in the universe, dating back nearly 13.8 billion years. It's not uniform. It's dotted with tiny fluctuations in temperature, variations that serve as fossil imprints of the early universe. By mapping these fluctuations, scientists can reconstruct the composition of the cosmos at its infancy. Satellite missions like COBE, WMAP, and most recently the Planck spacecraft have mapped the CMB in extraordinary detail. The results are both beautiful and unsettling. Embedded in those patterns is a precise measure of the universe's contents, a tiny fraction of ordinary matter, a significant portion of dark matter, and the majority made of dark energy. These measurements are not guesses. They are derived from direct observation and statistical analysis. The patterns are shaped by the interplay of gravity, pressure, and temperature in the early universe, and they tell a consistent story. Something unseen is shaping everything we observe. Gravitational lensing provides another window into the invisible. According to Einstein's general relativity, mass bends the fabric of space-time, and thus light itself. When light from distant galaxies passes near massive objects, like galaxy clusters, it gets distorted, magnified, or even split into arcs and rings. By studying these distortions, scientists can map the distribution of mass in the universe, even if that mass is invisible. The results are stunning. Lensing reveals vast halos of matter surrounding galaxies and clusters, structures far too large to be explained by visible matter alone. More recently, massive surveys such as the Sloan Digital Sky Survey and the Dark Energy Survey have used these and other methods to map the large-scale structure of the universe. What they've revealed is a cosmic web, a vast network of filaments made of galaxies and clusters, connected across billions of light-years, with dark matter forming the skeleton of this structure. Ordinary matter clings to the scaffolding of dark matter like dew on a spider's web. These cosmic structures, formed by gravity over billions of years, only make sense if dark matter exists and behaves as an invisible, non-interacting mass. Dark energy, meanwhile, leaves a different kind of signature. Its presence is inferred not through clustering, but through motion. Supernova measurements show the accelerating expansion. But scientists also study something called baryon acoustic oscillations, ripples in the distribution of galaxies caused by pressure waves in the early universe. These ripples serve as a kind of cosmic ruler, letting astronomers measure distances on the largest scales. The way these measurements shift over time confirms that something is pushing the universe apart faster and faster. That something, by every name and description, is dark energy. And yet, despite all this data, despite the increasingly detailed maps of matter, motion, and light, what dark matter and dark energy actually are remains a mystery. We can see their effects, we can trace their influence, but we cannot touch them, detect them directly, or reproduce them in laboratories. Particle accelerators like the Large Hadron Collider have searched for candidates like WIMPs, weakly interacting massive particles, but have found nothing conclusive. Other experiments using underground detectors have probed for interactions with atomic nuclei, but results remain inconclusive. The instruments are working. The measurements are sound. The mystery is real. We are not dealing with a failure of observation, but a confrontation with something outside the current framework of physics. Dark matter and dark energy are not gaps in our data. They are features of the universe that continue to defy identification, even as they shape every corner of the cosmos. As the data continued to accumulate, theorists began constructing models that might explain the nature of these elusive components. For dark matter, the central question remained: what kind of particle could account for the gravitational effects we observe without emitting or absorbing light? The standard model of particle physics, our best framework for understanding the fundamental building blocks of matter, offered no obvious candidates. None of its known particles had the right properties to serve as dark matter. This led to the proposal of entirely new particles, ones that would exist beyond the standard model. The most prominent candidates were WIMPs, weakly interacting massive particles. These hypothetical particles would be massive enough to contribute significantly to the universe's mass, and would interact with normal matter only through gravity and possibly the weak nuclear force, making them nearly impossible to detect directly. Dozens of experiments were designed to find them, from the deep underground detectors like Xenon and Lux to the high-energy collisions at the Large Hadron Collider. But despite years of effort, no WIMPs have been found. Other candidates emerged. Axions, ultralight particles originally proposed to solve a separate problem in quantum physics, became serious contenders. Unlike WIMPs, axions would have extremely low mass, but might exist in such vast quantities that their collective gravitational effect could account for dark matter. Then there are sterile neutrinos, hypothetical extensions of the neutrino family that interact only through gravity. None of these particles have been confirmed, but each represents a pathway towards solving the dark matter riddle. Some physicists have suggested that the problem isn't the particles, but the theory itself. What if gravity doesn't work the way we think it does at cosmic scales? This idea, known as modified Newtonian dynamics, or MOND, proposes altering the laws of gravity rather than invoking unseen matter. MOND can account for some galactic rotation curves, but it struggles to explain large-scale cosmic structures and observations like gravitational lensing. Still, it remains part of the ongoing debate, a reminder that our understanding of the universe may rest on foundations we have yet to fully comprehend. Dark energy, by contrast, demands a different kind of explanation. The simplest proposal is the cosmological constant, a term that Einstein himself introduced, then abandoned, only to be resurrected decades later. In this model, dark energy is a constant energy density filling space uniformly. As space expands, the amount of dark energy increases proportionally, leading to accelerated expansion. This idea fits observational data well, but it introduces new puzzles. The measured value of the cosmological constant is extraordinarily small, many orders of magnitude smaller than predictions from quantum field theory. This mismatch, called the cosmological constant problem, is one of the greatest unsolved issues in theoretical physics. Other models propose that dark energy is not constant but dynamic, driven by a scalar field that changes over time. These so-called quintessence models allow for varying behavior and might be tested through future observations of the expansion rate. Still others suggest that dark energy is an illusion, a byproduct of our limited understanding of gravity or the large-scale structure of the universe. Some models even entertain the possibility that the effects attributed to dark energy are the result of unknown interactions between dark matter particles, or that we're misinterpreting cosmic expansion due to unseen geometric properties of space-time. There is no shortage of creativity in the search for answers. New generations of observatories, like the Vera C. Rubin Observatory and the Euclid mission, are being built to study the cosmos with greater depth and precision than ever before. Their goal is not just to map the distribution of galaxies or measure the acceleration of space, but to test the very nature of reality, to challenge our assumptions about matter, energy, and the rules that govern them. In these efforts, mainstream science continues to walk the line between the known and the speculative, building models that are rigorously tested against observation, even as they stretch the limits of current theory. Theories rise and fall with each new dataset. A particle once favored may be ruled out by the silence of detectors. A constant once dismissed may become a cornerstone. This is the nature of science at the frontier. No certainty, only the pursuit of understanding amid shadows that still refuse to take shape. Yet even as mainstream models evolve, there remains a growing sense of unease among some researchers. The deeper the observations go, the more elaborate the theories must become to explain what's seen. At times, the complexity of the solutions begins to rival the mystery they're meant to solve. Despite decades of effort, no dark matter particle has been found. No unambiguous signal has emerged from underground detectors or high-energy collisions. And dark energy remains even more elusive. an invisible driver of cosmic acceleration with no clear source or mechanism. These gaps in understanding have led to a wider scientific debate, one not only about the nature of dark matter and dark energy, but about the tools and assumptions used to define them. Are we searching in the right way, or are we misinterpreting what the universe is telling us? Some scientists have suggested that our reliance on invisible components to explain observations may be masking a deeper issue. After all, dark matter and dark energy are defined not by what they are, but by what they do. They are placeholders for effects that can't be explained by known physics. This approach is not without precedent. Terms like phlogiston and ether once served similar roles in science, filling gaps in understanding until better models emerged. Could dark matter and dark energy be our modern phlogiston, temporary constructs awaiting a more fundamental discovery? This tension is especially clear in the debates over modified gravity. While mainstream cosmology favors the existence of unseen matter, some theorists argue that the gravitational anomalies observed in galaxies and clusters might not require dark matter at all, just a different theory of gravity. These ideas, from Mond to TVES, and more recent efforts like emergent gravity, challenge one of physics' most sacred assumptions, that gravity behaves the same everywhere in the universe. But modified gravity models face serious hurdles. They often work well on galactic scales but fail on larger cosmological scales. They also struggle to reproduce the detailed structure seen in the cosmic microwave background or the precise patterns of gravitational lensing. Nonetheless, their persistence highlights the broader uncertainty, an openness, however cautious, to the possibility that our current model of the cosmos is incomplete or even fundamentally flawed. In the realm of dark energy, the philosophical implications run deeper still. Unlike dark matter, which behaves like ordinary matter in terms of gravity, dark energy appears to act in direct opposition to it. It exerts negative pressure, driving space apart. This violates nearly every intuitive concept of how energy should behave. The very term energy seems inadequate to describe it. It does not clump, does not flow, and does not radiate. It simply exists, stretching the fabric of space itself. This behavior has led some theorists to speculate whether our understanding of space-time is missing a key piece, something more radical than a force or field, perhaps a property of geometry itself. The trouble is, no experiment yet devised can isolate dark energy. It reveals itself only through the large-scale motion of the universe. We can measure its influence with greater and greater precision, but its essence remains hidden. It behaves like a property of the vacuum, an inherent feature of space, but theories of quantum fields predict a value for vacuum energy that is wildly inconsistent with observations. This mismatch isn't minor. It's off by a factor of 10 poids, the largest known discrepancy between theory and measurement in all of physics. Such a gulf has led some scientists to consider whether the problem lies not in our measurements, but in our expectations. Perhaps the universe is fine-tuned, not because of chance or design, but because there are countless other universes where the constants are different. And only in a rare few, like ours, do conditions allow galaxies, stars, and life. This line of thought leads toward the anthropic principle and the concept of the multiverse, where dark energy's small but non-zero value is simply one of many possible outcomes. It is not explained. It is selected by the fact that we exist to measure it. But this explanation, while compelling to some, raises concerns for others. It leans heavily on ideas that may never be testable. It risks replacing one mystery with an even greater one, an infinite ensemble of realities we cannot observe. And it places human existence once again at the center of interpretation. Whether the answer lies in particles, forces, geometry, or something stranger, the question remains the same. What are these invisible forces that shape the fate of the universe, and why have they remained so persistently hidden? As mainstream research continues to dig deeper into the shadows of the cosmos, a growing fringe of thinkers has begun to propose more radical explanations for dark matter and dark energy, ideas that extend far beyond particles and fields into territory where physics brushes against metaphysics. These speculative models are not part of the scientific consensus, but they exist in the margins, where imagination and data sometimes collide in unexpected ways. One of the more provocative ideas is that dark matter could be evidence of extra dimensions. According to string theory and its related frameworks, the universe may have more than the familiar 3 dimensions of space and one of time. Some models propose the existence of hidden spatial dimensions, curled up at subatomic scales, invisible to us but potentially harboring their own physical laws and particles. In these scenarios, dark matter might not be composed of unknown particles in our universe at all, but of ordinary matter leaking in from adjacent dimensions. It would exert gravitational influence but evade detection by all other means. This would explain its apparent invisibility and its indifference to light and normal matter. Others have suggested that dark matter is not a substance, but a manifestation of topology, a structural feature of the universe itself. In this view, space-time may contain stable defects or distortions, much like cracks or knots in a crystalline lattice. These topological features could exert gravitational pull, acting like mass without having any particles at all. They wouldn't decay or radiate. They'd simply exist, dragging nearby stars and galaxies into motion without revealing themselves directly. Then there are those who propose a holographic origin for both dark matter and dark energy. The holographic principle, originally derived from studies of black holes, posits that all the information within a volume of space can be encoded on its boundary. If true, the entire universe may function as a kind of projection, our 3-dimensional reality emerging from 2-dimensional information. Some theorists argue that what we interpret as dark matter might be the residual effects of information compression or storage limits, distortions in the projected geometry of space-time. In a holographic universe, gravity itself could be emergent, not fundamental, and the invisible forces we track might be signals from the underlying code. This perspective intersects with even more speculative ideas, such as the simulation hypothesis. If reality is the product of computation, generated by a vast intelligent system, then anomalies like dark matter and dark energy may be artifacts of how that simulation is structured. The lag in gravitational calculations, or the accelerating expansion of space, might reflect optimizations in code or constraints imposed by the rendering engine. In this view, we are not discovering unknown forces but encountering the fingerprints of design. Ancient cosmologies, too, have been reinterpreted through the lens of dark energy and dark matter. Some alternative theorists draw connections between modern physics and ancient myths, seeing echoes of invisible forces in stories of celestial gods, spiritual realms, or sacred geometries. They argue that our ancestors may have perceived or intuited aspects of reality that modern science is only beginning to articulate in mathematical terms. While these interpretations are not testable in any traditional scientific sense, they reflect a deeper cultural pattern, the human drive to explain the hidden and the unknown. Other fringe researchers propose that consciousness itself plays a role. In quantum mechanics, the act of observation affects the outcome of experiments. Some have taken this to suggest that consciousness is entangled with the fabric of reality, that the mind and the universe are not separate, but intertwined. In extreme interpretations, dark energy becomes the backdrop of awareness itself, a sea of potential from which reality condenses through observation and interaction. While mainstream physicists dismiss these ideas as metaphysical speculation, they illustrate the depth of uncertainty surrounding these invisible phenomena. Despite their outlandish nature, these fringe theories share one feature with mainstream science. They arise from a sense of profound inadequacy in current models. The standard cosmological framework explains much, but not everything. The tools of physics grow sharper with each generation, but the substance of the mystery remains opaque. Whether through particles, dimensions, projections, or patterns of mind, these ideas represent humanity's attempt to stretch beyond the limits of light, reaching for a truth that continues to recede just beyond view. In the face of such profound mysteries, the question inevitably turns inward. What does the existence of dark matter and dark energy say about our place in the universe? These are not just scientific curiosities. They are revelations that challenge the very structure of human understanding. For thousands of years, human beings looked to the heavens and believed they saw the full extent of creation. The stars, the sun, the moon, the planets, these celestial bodies were once thought to be the totality of the cosmos. But with every advancement in observation, that view has been dismantled. First, we learned that Earth was not the center. Then, that our sun was just one among billions. Then, that our galaxy was only a small thread in a vast cosmic web. And now, we are told that all of it, all the stars and galaxies and nebulae, make up less than 5% of what truly exists. The rest is invisible, intangible, and yet utterly dominant. That is not a shift in scale, it is a shift in philosophy. For centuries, humanity has placed its faith in the power of observation, that what we can see, measure, and test is what is real. But the discovery of dark matter and dark energy forces a new perspective. We are surrounded by phenomena that cannot be seen or touched, that do not interact with light or matter in any familiar way, yet they govern the motion of galaxies and the expansion of space itself. This undermines the primacy of the senses. It suggests that the true nature of reality lies beyond human perception. There is a kind of humility in this realization, a reminder that we are limited beings, observing only a sliver of the whole. It invites comparisons to Plato's cave, where shadows on the wall are mistaken for the full shape of reality. It suggests that the universe, like the cave, holds deeper dimensions that we can sense only through inference, through the indirect traces they leave in the world we can see. This recognition does not diminish science, it elevates it. The fact that we can detect the gravitational pull of unseen matter or measure the acceleration of space itself is a testament to the reach of human inquiry. But it also shows us that knowledge is not a fixed destination. It is an ever-expanding frontier, with each answer pushing us toward new questions. Philosophically, the presence of dark energy, this mysterious force pulling the universe apart, has forced cosmologists to confront the notion of fate on a cosmic scale. If the acceleration continues unchecked, galaxies will eventually drift so far apart that light from one will never reach another. Stars will burn out. Matter will decay. In what's known as the heat death scenario, the universe will become cold, dark, and empty, a silent expanse dominated by entropy and isolation. This vision, while bleak, also reframes the value of the present. We live in a rare epoch, a moment when stars still shine, when galaxies are visible, when life is possible. The forces that shape the cosmos are not just abstract, they define the conditions that allow us to exist. If dark energy were slightly stronger or weaker, the universe might never have formed stars or collapsed before life could begin. This delicate balance hints at either immense coincidence or something deeper, perhaps a structure or logic that lies just beyond our comprehension. Spiritually, these mysteries echo ancient themes, the seen and unseen, light and darkness, permanence and change. Cultures throughout history have spoken of hidden realms, invisible forces, and the veil between what is and what is not. In modern physics, we find similar boundaries, not in myth, but in mathematics. The parallels are striking, not because science confirms the old stories, but because both traditions are responding to the same thing, the sense that reality is layered, that behind what is known, there is always more. Dark matter and dark energy are not just problems for physicists. They are reminders that existence itself is stranger than we thought, that the universe, for all its stars and galaxies, may only be the surface of something deeper, and that our quest to understand it is not just a journey through space, but a confrontation with mystery, one that forces us to reconsider what it means to know, to perceive, and to be. As the questions deepen, so too does the inventory of clues we've gathered over the past century, data points, theoretical models, observational patterns, all hinting at forces too vast and elusive to be contained by current scientific language. Though dark matter and dark energy remain nameless and formless in many respects, the body of evidence that supports their existence is no longer marginal. It is broad, detailed, and stubbornly consistent. We have mapped the rotation curves of thousands of galaxies and found nearly universal deviations from Newtonian predictions. Outer stars spinning far too quickly to be held by visible mass alone. We have charted the gravitational lensing of distant galaxies and seen the fingerprints of invisible structures bending light with a quiet precision. In clusters like the bullet cluster, where visible matter and gravitational mass appear spatially separated, we find some of the most direct, compelling evidence that dark matter is not simply a miscalculation, but a real, independent phenomenon. On cosmic scales, the distribution of galaxies forms a network, the cosmic web, traced by matter that does not emit light. Simulations run by supercomputers, modeling billions of particles over billions of years, produce structures that closely match the observed universe, but only when dark matter is included. Without it, the web collapses, and the large-scale patterns of reality fall apart. That alignment between simulation and observation, across such a vast range of scales, is not easily dismissed. For dark energy, the evidence is more abstract, but no less compelling. The brightness and redshift of distant Type 1a supernovae show us that space is expanding faster than it did in the past. This is not a glitch in the data. It has been confirmed through multiple independent methods. Measurements of baryon acoustic oscillations, gravitational wave signals, and the large-scale structure of the cosmos all point toward the same conclusion. Something is accelerating the expansion of the universe. The cosmic microwave background, the oldest light we can detect, reveals density fluctuations that match predictions only when dark energy is included in the model. The positions and spacing of these fluctuations form a statistical fingerprint of the early universe, and they fit remarkably well with a cosmos made of 5% ordinary matter, 27% dark matter, and 68% dark energy. These ratios are not arbitrary. They emerge repeatedly from the math, from different angles of investigation, from different epochs of cosmic history. Even the absence of direct detection tells us something. The silence of particle detectors rules out entire families of theoretical candidates, narrowing the search. The failure of modified gravity models to account for phenomena like the bullet cluster or the precise behavior of lensing arcs reduces the viability of alternatives. Each null result closes one door but sharpens the image on the doorway that remains open. And while there are discrepancies, tensions between measurements of the universe's expansion rate in the early cosmos versus the modern one, for instance, they do not eliminate the need for dark energy. If anything, they suggest additional complexity, new physics at work within the existing framework. The dark components of the universe are not figments of imagination. They are required to explain what we see, what we measure, what we can model and simulate with extraordinary accuracy. These clues form a puzzle that has yet to be solved. But they are real. They come not from a single observation, but from dozens of methods across decades of study. They involve gravitational forces, the propagation of light, the formation of galaxies, the birth of the universe itself. And through it all, the same silent partners remain: mass that does not shine, energy that does not pull but pushes, driving galaxies into motion, and the void itself to grow. We do not know what dark matter is. We do not understand dark energy. But we can trace their paths like shadows on the cosmic wall. And those shadows tell a consistent story, one in which the known is only a small island in a vast and unseen sea, a sea that exerts force, defines structure, and ultimately controls the fate of the cosmos. Each thread, pulled in the study of dark matter and dark energy, reveals yet another layer of complexity, reminding us that the universe is not obligated to be simple or even comprehensible. And yet, for all that remains unknown, what we do know has reshaped the boundaries of modern science. The presence of dark matter and dark energy has become a kind of silent scaffolding behind every major discovery in cosmology. It supports the architecture of galactic formation, it explains the expansion of space itself, and it drives the simulations that predict the evolution of the cosmos. The sheer consistency of the evidence is what makes the mystery so profound. It's not that these forces hide in obscure corners of the universe, they are everywhere. Every galaxy we observe rotates under the influence of dark matter. Every measurement of cosmic expansion reflects the push of dark energy. They are the dominant forces in the universe, not exceptions but the rule. And yet, they remain unseeable, undetectable by anything other than their gravitational influence. This realization has forced science to evolve, not only in the development of new instruments and experiments, but in the willingness to revise its own frameworks. The standard model of particle physics, once thought nearly complete, now appears inadequate. General relativity, one of the most successful theories in scientific history, may require revision or extension to account for dark energy. These mysteries have turned the cosmos into a laboratory for the unknown, where observation meets imagination and theory must bend to the will of data. It has also led to the development of new observational missions designed specifically to probe these forces. The European Space Agency's Euclid spacecraft, launched to map the geometry of the universe with unprecedented precision, aims to chart how dark matter and dark energy have shaped cosmic history over billions of years. NASA's upcoming Nancy Grace Roman Space Telescope, with its wide-field capabilities, is expected to survey vast swaths of sky to trace the imprint of these invisible forces on the distribution of galaxies and the bending of light. These efforts are not just about gathering more data, they represent a kind of existential engineering. Humanity is building tools to reach into the dark, to peel back the curtain on the largest and most elusive forces ever encountered. Each image, each data point, is a signal from the hidden structure of reality, a message encrypted in gravity, decoded in silence. Even the way we visualize the universe has changed. The familiar model of a cosmos filled with stars, planets, and glowing gas is now seen as incomplete. The true structure of the universe, the cosmic web of matter and void, is defined more by what we can't see than by what we can. Every bright point is a trace of something deeper, a lighthouse marking the presence of dark scaffolding beneath. In education, textbooks have shifted. Where once dark matter and dark energy were speculative footnotes, they are now foundational components in the standard cosmological model. The LCDM model, lambda cold dark matter, is the current best representation of the universe. It assumes dark energy, lambda, as a constant and dark matter as a cold, slow-moving form of mass that clumps and binds. And while it fits observations remarkably well, even this model is provisional, a working draft in a field where the ink never dries. The scale of the unknown is daunting, but it also reaffirms the value of inquiry. The more we discover, the more questions emerge. And with each unanswered question, we inch closer to something larger, a vision of the universe not as a closed system, but as an unfolding story. One in which we are both observers and participants. One where the pursuit of knowledge becomes a kind of cosmic pilgrimage. And in that pursuit, dark matter and dark energy are not just scientific challenges, they are metaphors for all that eludes us, for the unseen forces that shape not only galaxies but perhaps thought, perception, and purpose itself. They remind us that the greatest truths are often hidden in plain sight, waiting for the right mind, the right tool, the right moment to bring them into focus. Even as we stand surrounded by technology more advanced than any previous era, as we map galaxies billions of light years away and chart the echoes of creation itself, the heart of the universe remains veiled. More than 95% of its contents, dark matter and dark energy, cannot be seen, touched, or fully explained. And yet they shape every cosmic structure, influence every gravitational interaction, and dictate the long-term fate of everything that exists. In many ways, this is the great paradox of modern science. With all our progress, with all our instruments and theories, we still cannot answer some of the most fundamental questions. What is most of the universe made of? Why does it behave the way it does? What is the true nature of the space we live in? It is humbling, but it is also a gift, because it means the universe is still wild, still full of secrets, still waiting to be discovered. Dark matter and dark energy challenge our deepest assumptions. They force us to think in new ways, to question the boundaries of our knowledge, and to admit that for all we've learned, we are still peering into the unknown. They remind us that science is not a set of answers, but a method of reaching beyond what is comfortable, beyond what is obvious, into the places where imagination must meet evidence. They also remind us of our fragility, that the universe is not built for us, and yet somehow here we are, conscious observers suspended in a cosmos governed by forces we cannot see. We live in the thin margin between the very small and the very vast, between gravity's slow pull and energy's quiet expansion. And though we are dwarfed by the scale of what surrounds us, we are also the only known entities capable of asking these questions. capable of wondering what lies behind the curtain of reality. That curiosity, the spark that drives us to stare into the night sky, to listen for faint signals from distant galaxies, to imagine what we cannot yet explain, is perhaps the most powerful force of all. It is the light in the darkness, the one thing we know for certain, even when everything else is uncertain. And so we continue, with new telescopes, new theories, new questions, with humility and awe, with the understanding that what we know is small but growing, that the map of the universe is still being drawn, and that somewhere, out there, or maybe hidden all around us, the answers await. Thanks for listening. This has been Mysteries of the Universe. If you enjoyed today's episode, be sure to follow us wherever you get your podcasts. And if you'd like to support the show and unlock bonus content, subscribe to the Forbidden Knowledge Network on Patreon. Subscribe now.